Hello and good morning, class. Is my voice clear? Can anyone confirm this? Can you hear me?
Yes, sir.
Okay. So today we are going to start the topic of thick cylinders. In the previous lecture, we were studying the thin cylinders and we calculated the formulations for stresses and strains in the case of thin cylinders. But now we will move on to thick cylinders. So what is the major difference between thin and thick cylinders? In thin cylinder, actually, usually they are designed to carry heavy loads compared to the thin cylinder. And this is the reason that the provided thickness of the walls is greater than what we would provide in the case of thin cylinder. And to make a criteria to differentiate between thin and thick cylinder. In the case of thin cylinder, if you remember that the wall thickness was less than 1/10 of the inner radius of the circle. But in the case of thick cylinder, this wall thickness is more than or equal to 1/10 of the inner radius of the cylinder. So if you know the radius and thickness and you want to classify the cylinder, this is one best criteria to differentiate between the two. And also, if you remember, in the case of thin cylinder, the shear stresses were neglected. What was the reason for that? Because they were not designed to carry heavy loads. Therefore, the internal pressure was very small, and due to which the radial stress, which were equal to the internal pressure, were also small, and that is why we used to neglect these radial stresses. But in the case of thick cylinder, you will see that these radial stresses can't be neglected. They are relatively comparable to other two stresses, which are hoop stresses and longitudinal stresses. In the case of hoop stresses, which were acting on the thickness of the cylinder when we would divide the section into two parts, were uniformly distributed over the wall thickness. And the reason was that the wall thickness was very small compared to the, if this is the cylinder, and this, and this is someone's mic is so the hoop stresses, if this is the cylinder, and this is the wall thickness. In the case of thin cylinder, usually the wall thickness was very small, and that is why it was assumed that the hoop stresses are uniformly distributed over the thickness, because even if you calculate the hoop stresses at different points on the thickness of the cylinder, the mathematical value won't be much different at different location. But in the case of thick cylinder, the thickness is comparatively very large, and if you calculate the hoop stresses at different points along the thickness of the cylinder, you will see that the values are quite different from each other. And when you plot this value, they will vary in the parabolic manner. So that is this is one another difference between the workability of thin and thick cylinder. And common examples, that high pressure vessels or oil refining industries, they used to have the liquids at a high pressure to be stored in the cylinder. So that is why the cylinders that are used in such kind of industries are thick cylinder. And obviously, since there are so many complications, so the analytical solution of this kind of thick cylinder is pretty complex. And but since it's complex, so it will also be accurate as well. So actually, Gabriel Lame was one of the scientists who derived some expression to calculate the hoop stresses or longitudinal stresses in the case of thick cylinder. But before derivation, obviously, the exact solution is not possible in any case or in any mathematical problem. So there needs to be some assumptions to arrive at a solution that is practical and applicable for all the cases. By practical, I mean that it should be not too complex that a person who wants to apply has to do a lot of mathematics or has to spend too much time. It should be practical, but it should give reasonable answers compared to what is happening in the actual case. So for that, to make it practical, obviously there is a need to make some assumptions. So This scientist, that is named, he made some assumption to derive the solution of thick cylinder, and these were that the material of the cylinder is homogeneous and isotropic. By homogeneous or isotropic, it means that the material constants such as E or nu will be constant for one type of cylinder, and it won't vary with length or any other factor. And the plane section perpendicular to the longitudinal axis of the cylinder remain plane after the application of internal pressure. So what does this mean? If you remember, in the case of thin cylinder, we used to, if this was the cylinder and we used to cut the section, different sections at different locations, and we would have longitudinal stress. So one assumption in this case was, even if you take the section over here or here or here, at all these points there will be longitudinal stresses. So it was assumed that these three longitudinal stresses will be same on each section. So it won't vary if you change the location from where you cut the section. So if you calculate one longitudinal stress, it will be applicable for all the cross section. And the other assumption was all fibers are free to expand or contract independently without being. So that basically means that the expansion or contraction of the fibers which make the cylinder is independent of their interactive forces. That means that the bond stresses or the other internal stresses of the materials are neglected, and the expansion or contraction is strictly related to externally applied loads, which are the external pressure or the pressure exerted by the fluids that is flowing inside the cylinder. So now we'll be doing a derivation to determine the relationships for hoop stresses, longitudinal stresses, or the third one was radial stresses, just like we did in the case of thin cylinders. But in this case, it would be a bit different. So let's move on to the whiteboard. Now let's consider that we have this cylinder, which is a thick cylinder, and this is the wall thickness. This is the internal diameter, which is represented by, which has a radius of Ri, and this external diameter has a radius of R naught. This is the thickness of the cylinder, which I can represent by factor T. And this internal pressure, let's suppose that the cylinder is such that there is a force from outside as well, and there is a force or the internal pressure due to the fluid moving inside the cylinder. So the force due to external pressure is P naught, and the force due to the internal pressure is Pi. So we want to calculate or determine the relationships for hoop stresses, the radial stresses, and the longitudinal stresses in case of this thick cylinders. So we will assume a small differential area which is located at a distance of, or the average distance or average radius r. So we will assume a small differential element that is located at an average radius r, and this is our differential element. Now if I represent this differential element, or if I magnify this, I will get this kind of shape. Now it is important to understand everything about the shape, because if you understand this diagram, the next derivation won't be a huge problem. Now this top part of this shape is this one, right? And this bottom part of this shape is this one. Okay, so this is the small differential element. This is the length of this differential element, okay, which is shown over by the dashed line over here. And this is the top length. So since this is a differential element, and the distance of this part or this point from the center is r naught, which is this distance is r, which is shown over here as well, of this bottom point or the bottom layer. So this distance is r, which is shown over here as well, that the distance from the center to this point or to this layer is r. And similarly, the distance, since this length is, or this radius, since it is a differential element, so this radius over here is dr. So the distance from the center of the circle, or from this point to the top layer, is r plus dr, which is shown by this dr sign, which is the distance from this bottom layer to the top layer. Okay, so this length or the length which is going inside the cylinder is dx. Now in this example, we will assume that we are doing the derivation for the unit length. So wherever this dx is, we will replace it by a unit length. So the angle between the two sides or between the two curve shape is this angle, and it is represented by d theta. Okay, so obviously we know that on top and bottom of this layer will be the radial stresses, because radial stresses are directly are equal and opposite to the internal pressure, or in the case of external pressure, they will be equal and opposite to the external pressure. So on the top layer, this radial stress will occur, that is sigma r. If in the inner layer the radial stress is represented by sigma r, so in the top layer, obviously there will be some difference in the radial stresses. So that radial stress will be represented by sigma r plus dr. And hoop stresses, if you remember that the hoop stresses act perpendicular to the cross section. I will show you the previous picture from this figure. If you remember that this was our hoop stresses if we cut a cross section, and the hoop stresses are acting directly perpendicular to the thickness of the cylinder or to the cross section if you cut it in the on the lengthwise. Similarly, in this case, the hoop stresses should act perpendicular. But since this shape is a curved shape, basically, if you look from this figure, that this shape over here is a curved shape, so the hoop stresses are acting perpendicular to this curved shape, and it will have some angle with respect to the horizontal. So these are the hoop stresses which are acting on two of the faces of this differential element. And the other thing is that what is this area? This area over here on which the radial stresses are acting. So can anyone tell me that what is this arc length? This arc length. Or this. So this distance from this point O, let's call it as O, to the top is R plus dr, right? This R plus dr. So this arc length is basically R plus dr into d theta. But obviously this radius or this radial stresses are acting on this whole area. So the total area of this section or this curved area will be R plus dr into d theta, that is this arc length, multiplied by this width. This width is equal to dx. But since we have assumed that we will be doing this calculation for the unit length, so the total area will be r plus dr into d theta. So these radial stresses are acting on an area of r plus dr into d theta. Similarly, for this bottom area, or area of this bottom thickness or layer will be this length is r. So the arc length for this one is r into d theta, and the area is r d theta into dx. So since we are doing it for the unit length, so the area will be r d theta. Okay. And on this side, since this radial stresses are acting on this side, this area. Oh, sorry, the hoop stresses are acting on this area, which I will show by this blue arrows on this area, right? So what will be this area? This length is dx, the horizontal length is dx, and this distance is dr, right? So the area will be dr dot dx. So again, the dx is taken as 1, so area is dr. So we have got the areas. So if I want to calculate the forces, so what is force? Stress is equal to force over area. So the force will be stress multiplied by area. So let's show the front in this figure. This is basically the front view of the same figure. So the force that is acting on the top side will be this stress multiplied by this area. So this is the force or the radial force, I can call it, on the top face or on the top layer. So I multiplied this stress sigma r plus d sigma r multiplied by area. So this is the force that is acting on the top. And similarly on the bottom face, I will multiply this radial stress sigma r multiplied by area of this bottom layer, that is r d theta into dx. And for the face of hoop stresses, I will multiply this hoop stress by this triangular area, which is dr basically. So the hoop stress or the force in the hoop direction will be sigma h into dr. Similarly, on the left face, it will be sigma h into dr dot y. So any confusion about these figures, you can ask me now. If not, then we can move on to the next part of this.
सर ये जो एरिया रेड में लिखा है ये दोबारा समझा दो.
This area,
जो रेड में एरिया कैलकुलेट किया ना,
this
ये
one.
r प्लस जी ये वाला.
Okay. So what is this length? This arc length.
r plus dr d theta.
R plus dr into d theta. So if I want to calculate the area of this layer, so what will I do? I will multiply this length multiply by this horizontal length. This horizontal length is equal to dx, right?
Yes.
So this arc length is r plus dr into d theta multiplied by this dx. So this is for the top layer. I will write it here. So this dx is equal to 1. So this area will remain will be r plus dr into d theta, which is written over here, right?
Yes.
Any other question?
Sir, could you please once again explain the difference?
सर
Yes.
इंटरनल और एक्सटर्नल रेडियस का बता दें एक बार.
Look, this is the cylinder, and I have, let's suppose that you are looking it from the front side, right? So you will be since this is a thick cylinder, so this whole point or this whole thickness, this is the thickness of the cylinder. This is the inner radius. This inner radius is shown by Ri from this central point to this layer or to this point. And similarly, this cylinder will have an outer radius, which will be from the center point to this layer. Let me show it by red. So this radius over here is the outer radius, but we are taking our differential element at an average radius to this outer and inner radius. So this average radius is from the center point to this thickness, which is shown by these dotted lines or dashed lines, right?
Yes, sir.
Any other question?
Sir, can you please once again explain the calculations you did using the front view?
I cannot hear you properly. Can you speak again?
Sir, front view की मदद से जो हमने calculations की है वो एक दफा दोबारा.
Front view. Okay. So this simply I am showing the front view of this figure. So in this view I am showing the forces which are acting on this differential element. So I know the stress, which is sigma r plus dr, let's say on this top face, and I know the area of this face as well. So if I want to represent the force, what will I do? I will multiply this stress. If we have this relationship for stress and force, that the stress is equal to force over area. So if I want to calculate the force on this top face, I will multiply the stress acting on this face with the area, right? So the stress that is acting on the top face is sigma r plus d sigma r, and the area of this top face is r plus dr into d theta. So the force that is acting on this top face is the product of these two factors. Similarly, on this side, the hoop stress is acting, and the area on which this hoop stress is acting is this differential area, right? So I will multiply this area or this hoop stress with this differential area, that is sigma h, multiplied by area, which I have calculated over here, that is dr. So on the right side, I have shown this stress, sigma h into dr. Similarly, on the bottom face, I have the stress as sigma r, and the area is what? R into d theta. So sigma r, r into d theta. So this is how you determine the forces on each faces or in each face in the front view. Have you got it?
Yes, sir.
Okay. So I will just erase these things because we have to use these figures on the derivation. So Try to remember this. So from this figure, now I have two factors, sigma h and sigma r, and this is what we need to determine to calculate the stresses in the case of thick cylinder. So if I look at to this figure and write the equation for sigma fy, that is equal to 0. By the way, can anyone tell me that why this angle is also d theta by 2? Just think about it. So let me show you over here.
Alternate angle.
This angle, or I can just show it over here. This angle is d theta, right? And this hoop stress is acting at an angle of 90° with respect to this inclined surface. Now let's suppose we have another straight surface. Obviously this half angle will be d theta by 2. And if I have another surface, then this angle is also 90°. So if you calculate this angle, what will be this angle? This is the hoop stress. So what will be this angle? This angle will be 90 minus d theta by 2. Then what will be this angle? 90 minus into 90 minus d theta by 2. So 90 minus 90 plus d theta by 2. So these two will be cancelled out and will be left with this angle, which will be equal to d theta by 2, right? So that is why this angle of this hoop stress with the horizontal is d theta by 2. So now if I write the equation for forces in the y direction, I have one, this force, other one is this force, that is sigma r into r d theta, and the third force is this hoops, the y component, which is acting in the downward direction of this hoop force. So the equation will be sigma r plus d sigma r into r plus dr d theta minus sigma r into d theta, which is this downward force, and this component of hoop stress, that is minus sigma h dr dot 1 into sine of d theta by 2 equals to 0. But since there is a hoop stress on each face, so there will be another component which is acting on the downward direction on this right side. So I will write 2 over here because both of these components are equal in magnitude and also the direction is same. So I will simply write 2 over here. So now, since you know that this angle is very small, so we will take one assumption over here, that is sine d theta over 2 will be equal to d theta over 2. It doesn't make any difference. Also, the another assumption is that we used to do in such kind of analytical derivation is that when we are taking the derivative, it is a very small quantity. So the product of these derivative will also be equal to 0 because it will give us a small quantity in the result. So if I simplify this equation, I will get sigma r into r plus sigma r dr plus d sigma r into r plus d sigma r dr minus sigma r into r minus sigma h into dr, that is equal to 0. So this factor will be cancelled out with this one. This factor will be 0. So I'll be left with three factors that are sigma r dr plus d sigma r dot r minus sigma h dr is equal to 0. So if I divide this equation by dr, I will have sigma r minus sigma h plus d sigma r over dr dot r that is equal to 0. And let's call this equation as equation 1. So now if you remember that there was an assumption in the start that the longitudinal stresses or longitudinal strain in the case of thin cylinder are constant for different cross section. So in the previous class also for the thin cylinder, we made one relationship or we studied one relationship for different kind of strain. Let's say for the longitudinal strain, the relationship was, if I want to calculate the longitudinal strain, that will be equal to longitudinal strain minus the strain that are uh, very small, which are acting in other two directions, will also produce an impact or will also cause a reduction in the longitudinal strain. So the total longitudinal strain will be longitudinal strain minus strain due to in the hoop direction and minus strain in the third direction, that is the radial direction, right? So this factor or this equation is constant because it doesn't vary with different cross section. So if I simplify this relationship, I will get 1 over E epsilon L. For epsilon L, we will have sigma L minus nu sigma H plus sigma R, that is equal to constant. So now this factor is constant, and if I take this E on the other side, I will have sigma L minus nu into sigma H plus sigma R is equal to E into constant. So if I take this sigma L, because sigma L, that is longitudinal stress, is also constant, this nu will also be constant for one type of cylindrical element, I will be left with sigma H plus sigma R is equal to E into constant minus sigma L divided by nu, and negative sign of this nu will come over here. So basically Gabriel told this whole factor is a constant, right? Because everything in this one will have a single value for a particular type of cylinder. So Gabriel said that this whole factor is equal to 2a. This a is called as Lame's constant as per the name of Gabriel. So if you have one type of cylinder, you can determine or you will be provided with this factor A, which is determined based on the material properties or the cross-sectional properties, which are E and nu. You can calculate these factors and this constant will be provided. This sigma L is a constant which you can also calculate, and we will derive small relationship for that. And based on these factors, you can calculate this Lame's constant. And usually in the question, this constant is provided for a particular type of question. So if I substitute this value of sigma H plus sigma R in equation 1, I will get or I can just simplify it as sigma H is equal to 2a minus sigma R. So let's substitute this back in equation 1, which was this equation. So sigma r minus sigma h plus d sigma r over dr dot r is equal to 0. So I will substitute the value of sigma h into this one, and I will get sigma h, sorry, it should be sigma r minus 2a plus sigma r plus d sigma r over dr dot r is equal to 0. So I have this relationship, and if I rearrange this one, I will get d sigma r over dr dot r is equal to all these factors I will take on the other side. I will be left with 2 into a minus sigma r, because this sigma r will add up and will give you 2 sigma r minus 2a. So if I take this one on the other side, I will have this relationship. Now let's further simplify or rearrange it. D sigma r over this factor will come onto this side. So I will have d 2 into a minus sigma r, and this factor will go on to the other side. So I will have dr over r. By the way, I think we made a small mistake in this one. Just give me a moment.
सर सिग्मा एल के साथ पॉजिटिव नहीं है.
Positive sign with
सिग्मा एल.
sigma r, you mean? This one?
नो सिग्मा एल.
Where? On this side?
Yes. E minus e into constant plus.
Or we can
sigma
write
L.
it over. We can write it like this one, right? So the negative sign is this sigma L will go on to this right side. Okay. So if I integrate this equation, I will get, or this 2 we can take on the other side. Let's say it is on this side. So if I integrate this equation, I will have, so can anyone tell me what will be the integration of this term or this type of equations, if you remember?
log की form में.
Yeah. So the integration
log of r.
Of the left side will be log natural a minus sigma r. So the integral or the derivative of this will be minus 1. And on the right side, we will have 2 into log natural r plus a constant, which is c, right? So this minus will come outside, and we will have minus log natural a minus sigma r equals to, this 2 can go into the power. So this is the rule of logarithmic or log calculation. So this 2 will go into the power log natural r square plus c. So on the left side, if I take this on the other side, I will have log natural a minus sigma r plus log natural r square is equal to minus c. So again, there is one rule that if two logarithmics are being added, we can write them as a product. So log natural a minus sigma r into r square is equal to minus c. Now if I take the exponential on both sides, this log will be cancelled out, and this term on the right side will go into the exponent. So if I take the exponential, I will have a minus sigma r into r square is equal to e into e raised to power minus c. Now, again, there is one constant, which is this side. So Lame's proposed that this constant E minus C is equal to B. So now we have two constant A and B, and both of these are called as Lame's constant. So we will replace it with A minus sigma R into R square is equal to B. And if I simplify this equation, I will have sigma r is equal to a minus b over r square. So this is the relationship for radial stresses. And if I substitute this equation back into the equation number 2 that we have over here, if I substitute this equation, this is the equation 2. So if I substitute the value of sigma r into this equation, I will also get hoop stress for this cylinder. So this equation 2 is sigma h is equal to 2a minus sigma r. So substitute the value of sigma r into this one, that is 2a minus a plus b over r square. So sigma h is equal to, let's name it as equation 3. So sigma h will be a plus b over r square. So this is the relationship for hoop stresses, and let's name it as equation 4. In these two relationships, obviously we have related the sigma r or hoop stresses with the radius, but again, still we have these two constants. Now to determine these two constants, we can use the boundary conditions, or we can determine these relationships directly when we are solving the question. But this will be a bit tedious or complicated job for you to derive the relationship for different type of questions. So if we can figure out the values of these, in most of the literature, you will find the final relationships for the thick cylinder like this one. And in the question problem, they would apply the boundary condition and determine the values of these constant A and B first, and then they would calculate this radial and hoop stresses. But it's very convenient that if we solve these two constant and figure out one general relationship which would relate the given properties, for example, internal pressures or thickness or radius with this radial stresses. So we will apply the boundary condition during this derivation stage, and we will derive one generalized relationship which would be applicable for all the cases. So let's apply the boundary conditions to figure out these two stresses. So if you look back again in this figure, so can I say for this figure that at a distance of r is equal to ri, which is this distance, r, this is the radius obviously, so at a distance or at a radius of ri, the radial stress sigma r is equal to minus pi. Similarly, for a distance or for the radius of r is equal to r naught, the radial or radial stresses are equal to minus of this external pressure, because radial stresses are equal and opposite to the external pressure, or in this case we also have the internal fluid, so the radial stresses will be equal to the internal pressure. So this is one boundary condition for our case to determine these constant A and B. So we will apply this condition into our equation. So let's do that. So the boundary condition are that the stresses is equal to minus pi at r is equal to ri, and the second condition is that the radial stress is equal to minus p naught at r is equal to r naught. So I will substitute both of these factors in equation 3, which is this equation over here, for sigma r is equal to a minus b over r square. So when I substitute these into this equation, I will get minus pi is equal to a minus b over r I square, right? And the second equation, by substituting this second condition, I will leave it as 1 and 2. In equation 2, I will get, in equation 3, I will get minus p naught is equal to a minus b over r square. Now I have two equations and two unknown. This is r known. These factors will be known. So I have two equations and two unknowns that are a and b. So if I find out or figure out the values of these two constants, it would be very convenient to calculate the radial and Hooke's stresses. So I will just simply apply some mathematics, and that is, if I subtract these two equations, I will get minus pi. By the way, this is negative. So minus pi, and I subtract this one from this, so I will get plus p naught equals to, these two will be cancelled out, and I will be left minus b over ri square plus b over r naught square. So let's simplify it further. Minus pi plus p naught is equal to ri square r naught square, and this will be minus r naught square into b plus ri square into b. So if I take this b factor as common, or minus pi, I can write this negative sign can be taken as common. Minus p naught equals to minus b as common from here. So inside I will have r naught square minus ri square over ri square r naught square. So these minus sign will be cancelled out, and the relationship for b will be equal to ri square r naught square pi minus p naught over r naught square minus ri square. So this is the expression for the constant b. But again, still I need to find out the expression for the constant a. So I will substitute this b factor into this equation 5. Let's call this as 5. So that is minus pi is equal to a minus b over ri square. So I will substitute this b in equation 5. So what will I get? Equation 5, I will write it again. That is minus pi is equal to a minus b over ri square. So the factor a will be equal to b over ri square minus pi. So by substituting the value of b, we will have r naught square pi minus p naught over r naught square minus ri square. Obviously, over here we have ri square and over here we have ri square, so they will be cancelled out, minus pi. So again, let's simplify this one to have a simple expression. So we'll get a is equal to r naught square pi minus p naught divided by r naught square minus ri square minus pi r naught square plus pi ri square. So if you simplify this further, this factor will be cancelled out with this one. So we will be left with A is equal to Ri square Pi minus R naught square P naught over R naught square minus Ri square. So this is the expression for A. Now if I substitute, now I have the values of both A factor and this B factor, which are both constant in terms of internal radius, external radius, external radius, internal pressure and external pressure. So I don't have to apply the boundary conditions for different type of question. So if I substitute this value of A and B into these equation 3 and 4, substitute A and B in equation 3 and 4, I will get this sigma R and sigma H. So I'm not doing this simple derivation. Actually, it's a simple step. You just have to substitute the values of A and B into this equation and you can calculate sigma R. So I have given you the final expression that you are going to get by this substitution, which is shown over here. So you just have to substitute the values of A and B and just do some small mathematical rearrangement and you will get this final expression for sigma R and sigma H. Now in this expression, if you see that if you know the internal radius, you know the internal pressure and external pressures or the external radius, then you can simply substitute these value into this equation and you can calculate this value of radial stresses and Hooke stresses. But still, we need to answer two questions. First, we need to figure out that whether sigma R is comparable to sigma H. For example, in the case of thin cylinder, this sigma R is very, very less compared to sigma H or sigma L. So we neglected it. So we will see that in the numerical problem that whether it is comparable to sigma H, that we should not neglect it. And the second thing is that we need to look for the distribution of sigma H. So we will calculate the values of sigma H at different points along the thickness or along the radius, and we will figure out that whether its thickness is really parabolic or it's just simply an assumption. So this I will leave up to you to calculate, or you just have to substitute the values of A and B and you will get this expression for sigma R and sigma H, and I hope you can do it. So let's come back to these slides. Actually, this derivation is given in the slides as well, but it's better that you do it by yourself for understanding. So there are two special cases as well in this derivation. Obviously, we have derived the relationship for sigma R and sigma H. So if there is a case that when this P naught or this external pressure is 0, you will automatically have an expression of sigma R in terms of Pi, Ri or R naught square or Ri square. But there are sometimes special cases where they have derived the relationship based on these boundary conditions. So I will leave this one to you as well to derive these small relationships. You simply have the equation for sigma H in terms of A plus B over R square or whatever it is. So you have the relationship. Now we applied in our case, or in the derivation we did, was the same boundary condition that R is equal to Ri, sigma R is equal to minus Pi. But in this special case, let's consider there is a thick cylinder with internal pressure only. So that means that at a radius of R is equal to R naught, this radial stress will be equal to 0. So this is our second boundary condition. So using these two boundary conditions, we will determine the values of A and B, and which will come out to be these values. And you substitute these values into equation 3 and 4, and you will get the equation for radial and Hooke stresses for this special case in which only the internal pressure is acting. So you just have to do the same procedure and you will get the expression for radial and Hooke stresses. But obviously it's not necessary, because you have this one expression for the generalized case where even the outer pressure is 0, you can directly compute the stresses. And similarly, there is another case with external pressure only. So in this case, if I write the boundary condition, what will be that at R is equal to Ri, sigma R is equal to 0, and similarly at R is equal to R naught, sigma R is equal to minus P naught, or you can call it as minus P alone. So again, by applying these two boundary conditions, you will figure out the values of A and B and substitute these values in equation 3 and 4. You will get these type of relationships for the calculation of radial and hoop stresses. But the important thing is, first you need to understand each and every step of our major derivation. Then you can apply this boundary condition, or you can implement the physical phenomena, or you can understand the physical phenomena behind these conditions. So I would suggest you to go through all the derivation that we have just did, and then you can apply this special cases. And the final thing is, obviously we have determined the longitudinal and hoop stresses, but still, we determined the radial and hoop stresses, but we didn't determine any expression for the longitudinal stresses. Obviously, they are constant for different cross section, but we need to figure out what is its value on one cross section. Then we can use the same value for all the cases. So for longitudinal stresses, let's suppose we have this cross section or this. Is there any question?
Yes sir. सर ये बहुत ज़्यादा हेक्टिक हो गया है पिछला वाला, ये कल ना करने लगा न्यूटन स्ट्रेसेस, क्योंकि रूट स्ट्रेसेस और रेडियल स्ट्रेसेस बहुत ज़्यादा हेक्टिक हो गया.
I can't hear you properly. Can you speak again?
सर रेडियल स्ट्रेसेस एंड रूट स्ट्रेसेस बहुत ज़्यादा हेक्टिक हो गया डेरिवेशन के समय. सर ये कल ना करने लॉन्गिट्यूडनल स्ट्रेसेस, क्योंकि अब बस समझ आना खत्म हो गया.
If someone can understand his question, can he explain it to me? I really can't hear his voice properly.
सर 12 बजे क्लास है, ये बता रहे हो.
Okay, this is just one step derivation. It's not a big derivation. So it's better that if we discuss this right now, so things will be convenient. It's just these two steps in this derivation for longitudinal stress. So let's suppose that this is the cross section of this same cylinder, and with a thickness T, on which this longitudinal stress, if you remember from the thin cylinder, because these longitudinal stresses are acting on the thickness of the cylinder. So these longitudinal stresses are acting on this thickness, that is sigma L, and these two forces are Pi, and this forces or the external force that is acting is P naught. So we will simply have to apply this relationship, that is sigma Fx is equal to 0. And to find out the forces, again we have to apply the similar concept, that multiply these stresses with the area on which it is acting. So if I apply sigma Fx on this Pi is due to the internal fluid, and it is acting on the internal cross section. For example, it can act over here, or let's suppose it is acting on this wall of the cylindrical element. So this Pi is acting onto the internal area of the cylinder. So over here, if you see that Pi multiplied by internal area will give us the force due to the internal fluid. And similarly, this P naught is acting on from the external side, so it will be acting on the whole diameter or on the external radius of the cylinder. So I will multiply this P naught with the external radius, that is, or with the area due to external radius, that is pi into r naught square. So I have two forces on the x direction, this Pi and P naught, and the third force is obviously this sigma L. So this sigma L will be acting on this thickness only. So to calculate this area, I will simply calculate the area of this outer cylinder or the outer radius and the inner radius, and if I subtract these two areas, I will get this area for this thickness. So what will be this area? It's simple, that you have to multiply this longitudinal stress multiply by this area, which is the difference between the two areas, and it will give us this area. So if I rearrange this expression, I will get the expression for longitudinal stress, that is P naught R naught square pi Ri square over R naught square minus Ri square. So if you know the outer diameter, the internal radius and the outer radius, you can figure out the longitudinal stresses for thick cylinder. So this is it from the derivation. So now you have the expression for all type of stresses. Try to review this derivation as a whole, and if you have any question, you can ask me now, or later you can send me a message.